So let's start the session. Thank you for all the participants who has given their time to join this training session. So I would like to share my screen. So very good morning to all of you once again. It's my pleasure to join this session today. Myself Anil Sharma from Impulse Technology. So there will be a two session today from 11 to 1 p.m. and another session will be from 2 to 4 p.m. So first half, in first session, we will cover about the presentation, user interface, small material modeling, and some other demonstrations. In second half, you can also go for the demonstration, for the training, or you can also make the practice in your particular computer. Since we already given the download link of the software and the license file. Those who have not get it, they can download from the chat box that I already shared few minutes back. So let's get started. You cannot unmute your mic. You can also ask your query after the this first sessions. So I will take your query in the once I finished my presentation and demonstrations. So I would like to introduce about this Impulse Technology. Impulse Technology is an Indian company that we are located in Gurgaon near to Delhi, and we are representing this Nano Academic Technology, which is a Canadian company which provide the simulation software for nanoscale atomistics material devices, semiconductor devices, and quantum technology simulations. Whatever you have learned, got the emails information related to that product, we will discuss about from this Nano Academic Technology. This is our partner company, Nano Academic Technology, which provide the material modeling, device modeling, simulation, graphene, carbon nanotube, crystal molecules, and quantum technology simulation tool. For solar cells related application, perovskite, tandem, hybrid, thin film related application, we have this Fluxim, that is another partner from Switzerland, which provides solar cells and LEDs related applications. Today we will discuss about this Nano Academic Technology. Even we also provide the micro probe stations for characterization of the samples. As you have seen the demo short video where you have seen some vacuum compatible chamber and micro probe station where synthesis, characterization, simulations, we have all domains of product related to nanotechnology, semiconductor, and quantum technology product. Now let's come on to the main agenda that we have discussed in the meeting. So we will concentrate about Nano Academic Technology, that is our parent company, which is based in Canada, and it is founded in 2008 by Dr. Hongo, Dr. Zhu, and Dr. Lee from McGill University. It was developed for molecular quantum transports, quantum transport, NEGF device simulation, material simulation, and with advanced modeling tools for digitalizations and quantum technology, the revolution that is an emerging sector for spin qubit semiconductor devices. Then this quantum TCAT tools we are also offering. Even new innovative tools are developing, new features are keeping developing by the industry continuously. This is the introduction about our parent company. Now, if we go for the next slide, that we have the today agenda, because the things which you are looking, that is specifically for nano related applications, atomistics, material devices, solar cells, photoreactor. For that purpose, we have the product called RESCU and NanoDCAL. So RESCU is basically for material simulation, and NanoDCAL is for material as well as device simulations. These are two very effective tools which can help you to boost your research in your particular niche. So this tool will help and solve different problems, and it will work on realistic physics, and it will solve the complex materials and device application, including the transistors as well. So let's go in the coming slides and we'll discuss what application the tool can cover up. So if we talk about this NanoDCAL tool, which will work on material as well as device applications. So you can see here, this is Nano DFT calculator. The NanoDCAL tool is a Nano DFT calculator. It works on density functional theory. Density functional theory itself is a very broad topic where you can characterize simulate your material based on theoretical predictions. So based on DFT plus NEGF theory, it will solve the different equations, Phonen equations, DFT equations, and many more other equations will be solved in the background calculation engines. This code is basically written in MATLAB and C. MATLAB and C both are in the combination, and this code, this NanoDCAL calculation engine, is used in many of the publications. You can simply type NanoDCAL on Google Scholar and find a lot of papers related to this particular product. It majorly works on materials modeling, devices modeling, and transistor modeling, including the gate controlling IDBD characteristics. That is also possible. So either you want to work on 2D material, any type of 2D materials, you can work on it. 2D material based device application, where you can define some electrode, anode, and cathodes, and you can apply some biasing on the terminal, and you can calculate the IDBD characteristics, including if you want to add the channel or that gate regions, then it is also possible. You can also define the transistor, gate controller, and crystal, molecule, devices, interface, heterostructures. In all the domain, the software tool can work. So this is a brief idea about this NanoDCAL. If we go about the second product, that is called RESCU, that works on DFT along with DFT. The earlier product, NanoDCAL, works on DFT plus NEGF. DFT plus NEGF, quantum transports calculation. And this particular tool will work on DFT along with DFT, density functional perturbation theory, which will solve the complex Phonen equations, and it will solve the electronic property along with the perturbation theory, which will calculate the response function, polarization, Phonen property, optical property, Raman property for large number of material simulations. If you work on only materials application, no device simulation, then RESCU alone tool can be best fit for your research. Where this RESCU will solve your complex problem. Let's suppose you want to simulate 5,000 atom, 2,000 atom, 10,000 atom, then definitely this code will help you to simulate on a more number of atoms, and it can calculate the DFT implementation is there, where dielectric tensor, dynamical matrix, optical property, dielectric permittivity, refractive index, real and imaginary part of refractive index can be calculated. Raman tool is there, tensor, spectrum, intensity. With the hybrid functionals are introduced. In this NanoDCAL and DFT, that works specifically for device application. But this will work on hybrid functionals, exchange correlation functions with the Hubbard U terms, with the DOS, PDOS, LDOS, PLDOS, band unfolding, band structure, charge analysis, non-linear optical susceptibility, Spintronics, Phonen calculation, large scale CFSI solvers. So for optical, Raman, dielectric, hybrid function, and perturbation theory, in that purpose scenario, this RESCU tool will be required. So these are two code. One is NanoDCAL, second one is RESCU. Both are background calculation engine that will solve the equations in the background, and it will calculate the material or device properties. If we go in the details, what kind of materials, what kind of devices it can simulate or it can model. Basically, it works on molecular structures, graphenes, benzenes, or any molecules. There is a molecular builder will be there, where you can also build the complex molecules as well. So molecular builder will be there, molecular building based devices will be there, where if you build the molecule, you want to connect with the electrode, metallic electrode, you can connect the molecule with the electrode. As you can see, the bottom or top electrode you can specify, and that can form the device applications. You can make the surfaces also. If you want to define some plane, some 100 plane, 001 plane, 111 plane, or that Miller indices, some vacuum you want to create in your lattice. So that surface structure in particular planes, you can also define and get it simulate the nanowire or other applications, including the complex material where tetragonal, hexagonal, triclinic, rhombohedral, different lattice parameter you can define by yourself, or you can import the material files as well. And 2D material based devices, if you have want to work on graphene based device application, then definitely it is possible. You can make the graphene sheet and you can define some electrode, apply some biasing on the right side or left side, and then you can plot the IV characteristics or photocurrent, photodetectors applications, or other material characteristics as well. So firstly, simulate the material, then material can be converted into the devices. If you want to work on interface structure, some heterostructures kind of application, then there is a possible. Let's suppose you want to make a metal interface or metal or semiconductor interface properties, or semiconductor interface, silicon germanium interface property, you would like to work on it, then interface structure is also possible. Even other complex material, whatever you would like to build, there is a sophisticated user builder is there, which will help you to build the structures as per your convenience. I will show you in the lab demo how it can be done in the tool. You have to keep patient and concentrate on the training so that you will learn various kind of things today. Now, if we talk about what kind of property, what kind of builder, what kind of setup calculator is there are three things for any in any of the software. One thing is that pre-processing, where you can define the input, where you can model the structures, you can define your atomic structures, crystals, molecule, devices, and you can manipulate in your structures according to your convenience. You can introduce the doping, defect, or particular sheets you can create, or vising you can apply. That's why these advanced building tools are there. This advanced building tool will help you to build the structures. Once your structure is ready, your material is ready, or your device is ready, the next part it goes to the simulation engine that will use the theory, on what basis the software will run the job. The software will do the calculations. So here basically it will works on density functional theory, density function perturbation theory, and non-equilibrium green function quantum transports method. In that basis, you have to define some k-point sampling, exchange correlation functions, electron temperature, energy cutoff, basis sets that need to be defined in setup calculator, user-friendly input parameter. And once the software done the calculation, then post-processing, that is a visualization of your output. So there is own output visualizer is there, where you can visualize whatever the you have selected the calculation parameter. Software will run the job and then generate some output file which you can visualize in the output. So various material property, including electronic, structural, optical, thermal, magnetic, electron thermal coupling, including the device properties as well. If you want to calculate device property like photocurrent, IV characteristics, or some density of state of the device, thermoelectric currents, and many more property will be there. I will show you in the lab demo once I will start the training sessions after this presentations. And those who works on other application from the nanoelectronics to move forward for the Spintronics related application, then movement of our atom positions, atomic coordinates, spin movement, electric spin, you can apply electric field or spin orbit couplings, spin orbit interaction, some rho theta phi, you can twitch the angles that you can twitch the angle on particular orbit things. So there is spin movement is there. You can interact the ions with your graphene sheets or any other material sheets. The interaction with a particular atomic sheets can be done. Passivations can be done. So for that lower power consumption, higher power density, improve the device performance, spin related application that is also possible. Nanoribbon intrinsic with magnetic effect, electrical effect, some stress you can apply, stretch the cells so that electromagnetic or light you can fall on different condition and you can do the studies. And if you want to work on batteries related applications or photogalvanic related application, then it is also possible, where either you want to work on single layer structure of the material, or bilayer structure of the material, or tri-layer structure. Like as you can see in the picture, there are 3 layers. One boron nitride layer, graphene layer, and boron nitride. Boron nitride, the graphene is sandwiched in between 2 boron nitride layers. And then you can also simulate this 3 layer lattice materials. If you want to define some electrode, that is also possible. So you can see the material is simulated and band gap is calculated. Indirect gap, band gap, direct band gap with spin up, spin down, magnetic movements, some armchair, zigzag, armchair, Kral vectors of particular parameters. This lattice of this particular unit cell crystal you can define and find the electronic property, and device property will also become possible. Now this is for material and 2-terminal device. If you will go for 3-terminal device where you want to define some electrode, where you want to define some gate. So as you can see in this picture, this is 3-terminal device where left metallic electrode, right metallic electrode. In between there is a channel region. There a green molecular layer is there in between the electrode, which is connected by this gate terminal. And you can see in graph A and B in 2D, this is molecular 1, molecule 2, and this is electrode type. And accordingly, we have tried to simulate based on 2 different molecules what will be the effect on the device transmission coefficient or IV characteristics. So this transmission spectrum is plotted at molecule A and molecule B. So with different minimum energy and maximum energy range, what will be the transmission coefficient that you can calculate and predict it. So this will work on, it is not specifically on only molecule or only crystal. There are some software exist which only work on particular specific problems on only molecule or only material. But this is a complete solution where either you want to work on crystal structure, or you want to work on molecular structure, or you want to work on device structure, 2-terminal device, including the transistors. So all packages are included in the same tool. Now, if you want to work on multi-probe device structure, let's suppose there are 4 terminal or 6 contact in your device. There is top contact, bottom contact, front contact, back contact, left contact, right contact. 6 probe device, as you can see in this picture, around 6 probe can be defined. And whatever the terminal you would like to apply the device, you can apply according to your convenience. You can see this is some vertically, horizontally. So we can connect the electrode here, we can connect the metallic electrode here, this left side, right side, and front and back in G direction. We can also apply. We can also twitch on particular angle. Let's suppose you want to work on flexible devices. So that flexible electronics is also possible, where you can move the device one side or both the sides on particular angle, so that device can be flexible on particular radius or particular that angles. And accordingly, you can plot the band structure, conductance, AC characteristics, modulus, and Phonen calculation, thermoelectric properties, and many more will be there that we'll discuss shortly. So as I have introduced about the presentation session about this nano academic bottom one atomistics material and device simulation tool. So NanoDCAL and RESCU I have introduced. Plus version is about to come with the within 1 year or 2 years, that is under development in Python language. And for qubit application, quantum technology, that QTCAT tool is there. It works on quantum technology, computer-aided design applications. Those who work on solar cell application, you can see there is SATFOS, LAOS, PIOS, PHILOS, LITOS, LITE. These are all these are 2 software, SATFOS and LAOS. SATFOS works on one-dimensional solar cell perovskite tandem thin film application, and it works on module simulation, AMOLED simulation, large area applications. This is measurement of IV measurement, impedance measurement characteristics, and it is ELPL, electroluminance, photoluminance measurement, degradation analysis of LED application, stability of perovskite analysis, For that purpose, this Fluxim, that is another partner which provide the equipment as well as the software for characterization or simulation related to optoelectronics applications. So this is completely domain that we are dealing with that. If anybody works on experimental parts, we also provide the micro probe stations. Micro probe stations for thin film application. We provide the octagonal micro probe station with the stainless steel 316 with very work that loaded high weighted this micro probe station is there. Those who works on experimental, they can put it their sample. It is vacuum compatible with the temperature, humidity, pressure controller, and light. We can also fall the one sun light on the device, and we can also do the characterization of your material, experimental synthesis and material characterization probe station, including the sample holder, which can measure up to 6 pixel, 8 pixel. That's why there is another company called LASC. It is Indian made indigenous product for micro probe station, where you can control the probes, and you can there is tungsten probes are there which can put it on your sample, and it can also do the characterization, experimentally characterization of the sample application. There is tungsten probe will be there. We can customize this probe stations also according to your particular needs, particular requirement on different temperature. You want to study how your sample IV characteristics will be there, impedance measurement will be there, or light can also be fall the intensity on this vacuum compatible micro probe station. That is possible. We can also provide you the chiller for cooling the that sample, and no LN2 liquid nitrogen is needed. From -30 to 200 degrees centigrade, it can work easily. And custom made software will be there to for the analysis of your property, and BNC character is there, and for light pogo pins are also there. So that crocodile pin which you connect, maybe those who work on experimentally, that can be obsolete. We can use the pogo pin or the tungsten also, so that no shadow or other effect on your seat resistance on the device applications. So this is a portfolio of the product that our company Impulse Technology is representing in India. Some of the people maybe works on different application. As you know, around 100 for more than 100 people have joined this training session today. So different people may have different requirements. So thank you for concentrating about the presentation session. This is my particular contact information. In future, you need any specific according to your particular requirement. You can drop the email, or you can call us, you can WhatsApp us, you can send your requirement according to the whatever the product problems you are working on it. So thank you for giving this time to listen the presentation. We will go for the live demo, and once my talk will be finished, then we will ask your queries as well. In the meantime, if you want to put it your questions, you can type in the chat box. So let's get start in the second that demonstration part. So as you know, the software is installed in C drive. Everybody may have installed in C drive. Wherever the location you have installed, that is not problem. You can go to the particular folder. So let's start the session. I will go your query session in after this finished by work. So I will go to the C drive where my software is installed, and then I will go to this device studio 2022 and go to the bin folder where my software is installed. And there is a folder called device studio. I would like to open it. So here you can see I open it. You can see the user interface is opened. Here there are two options. One is to create from scratch, or you can open the existing project. If you work earlier, you can open the existing project. If you want to work from beginning, just click on create new project. Now I will click on create new project and click on OK button. Would like to define my name of project. So let's suppose whatever the name of my project, Nano as an example. I want to give the name of my project and save it on desktop. Now you can see this is a user interface. Participant, those who have not downloaded or not get the download link, you can contact to us later after this demo part. We can provide you. Initially, just concentrate on the training session so that you will learn something. Now here you can see there is an option called file option, where multiple options are there. You can open your existing project or you can create the new project. Now you can see here there is a particular there are three options. You can make the device, you can make the crystal, or you can create the molecules. So first of all, instead of creating my material from scratch, I would like to import from my library. So there is import button. I can import from local where my software is installed. So my software is installed in C drive and device studio program file like that. From there, I can load the material. I will click on import local. So in my computer, where this the software is installed, there is a material library where all molecule, crystal, material, devices, 2D material, topological insulator, all are there. So when I will locate particular folder, you can find the information. You can find the information of different material inside these particular directory. So either you work on conductor, insulator, layer material, magnetic material, metal oxide, novelty material, semiconductor. These all materials are there. So I will go there. You can see there are couple of materials are there. So whatever material you are working on it, you can select according to your convenient. Initially, as an example, let me select silicon. There are other extensions also there. You can see HZW, XYZ, CIF, XSD, Postcar, Quantcar, SCF input, relax.json. These all formats are possible. If you already have the input file in these particular extension, you can directly upload on the tool. I would like to upload by this HZW. But if you have a zip format, crystallographic information, CIF file, you can upload. PY file is also possible. And other XYZ format is also possible. So I click and load it. And you can see here, I can maximize it. My crystal silicon is added in my dashboard. This is single unit cell of 2 atom crystals. Okay. Now you can see we will try to simulate it. We can rotate it. This is particular rotate option, 3D viewer. Once you will click on it, you can see the rotate on particular dimension. Whenever your crystal structure is big, then you can rotate on particular angles. Now this is for select purpose. Whenever you will click on this select, it will select it. You can make it home by this view screen. If you want to view in XY plane, XZ plane, YZ plane, YX plane, ZX plane, so different plane you can visualize according to your convenience. Now I have simply imported this material from my library. If you don't want to, if your material is not present, then you can upload your own material file on the particular tool. So you can see here, this is import button and import local, where different extensions are there. You can browse in your computer where the material, your existing materials are present. You can also upload that material. Now I will try to simulate this material. As you can see, there are a lot of options are there on the toolbar. These options, once you will particularly click on this, these will help you a lot for building or making any kind of structures. In this left side project window, that is for input and output. This bar is for property, where it will display the information about the unit cell. What will be the coordinate point? What will be the vector ABC? What will be the total number of atom in this particular unit cell? Total area of the lattice. The property of this particular crystal, that will display in this left side property bar. This particular area is dedicatedly for input and output file. Bottom one area, which you can see, that is job manager. That is basically for the calculation log bar, where the simulation will be so that your input simulation is running. Now, if we run the job, you can see there is a simulator option. NanoDCAL, we will discuss first NanoDCAL, then RESCU. So there is option called NanoDCAL. I can go there and click on SCF calculations. This is SCF stand for cell consistent field calculations. Once I click on SCF calculation, there is electron temperature, energy cutoff, exchange correlation function, LDA and GGA. Basic functionals are given in NanoDCAL. If you will go for hybrid and meta GGA, some HSE, HSE 06, then RESCU, the material modeling dedicatedly for material simulation, RESCU code will be helpful. So whatever the exchange correlation you require, that you can define. This is number of K point sampling. So in N1, N2, N3, X, Y, Z direction, the number of sampling point you can specify. And then go to the iteration control, which will solve the Hamiltonian equations, density matrix, maximum steps, Poulet method. So the Hamiltonian equations will be solved, and it will solve the calculate the total energy. This is basis sets, where double zeta polarized, single zeta polarized, single zeta double polarized, double zeta single polarized, or Howard atoms is also there with SPDF by element or by atoms. You can include the Howard atoms as well. As you can see, the only silicon material is there in the crystal. That's why the silicon basis sets is included. So LDA DZP, double zeta polarized with PVE DZP. If you want to upload your own basis sets, then you can go to the user defined, and there is a library called neutral atomic database. In this neutral atomic database, this is a library of different material, where different material have different basis sets, single zeta polarized, double zeta polarized with LDA, PVE, that exist in it, that, and you can upload according to your convenience. Now, once it is done, you can go to the next tab, that is called spin related application. If somebody work on Spintronics, collinear spin, general spin, without spin, then enable particular feature and define the spin polarization, or select the general spin, select the rho, theta, phi, and include the spin orbit interaction that you can choose if you want to include. Initially, I would like to simulate without any spin effect. Whenever you will like to include the spin, the simulation time may increase. As you know, the DFT, density functional theory, it takes time in the simulation. It also depends on the system, that configuration of your computer, as well as the license type that you are using. So I select this without a spin and click on generate file option. Once I click on generate, you can see there is a silicon folder, NanoDCAL crystal folder has generated. Here you can see the scf.input file is there. I will right click and click on run button. So just right click and click on run. You can see the software can also run in the parallel, but in the trial version, it will run on the single core. Either you have a very good system, but the software will not utilize because it is free license and trial license, and the software is commercial license version which need to be purchased later on. So you can see here I will initially run it on one parallel core and click on run button. Once I will click on it, you can see the job manager in the bottom of the page, the calculation showing running. So it is loading the parameter. It is running the calculation. If you want to stop the calculation, this action you can take stop. You can see the progress once the calculation is started. So calculation will start here shortly in this silicon job status. Job calculation status will be displayed once all processing of the input is completed. So it will start shortly. You can see the log.txt file is generated and it has loaded the parameters and calculation is going on. In the meantime, if you want to select the analysis part, you can go to this simulator and select the analysis. Analysis in the sense what property you want to calculate. What property you want to calculate. So you can go to this analysis option and here you can see what property you can calculate, that is called density of state, effective potential, total energy, band structure, charge, Hessian, phonon band structure, electron density, potential, transmission channel, eigenstate, full band structure, effective mass, complex band structure, ZT, full phonon band structure, phonon density of state, modulus, and many more is also there. These are only crystal, only material specific property. Whenever you will go for the device, whenever you will create the device in the tool, then device property will be extra. That is IV, photocurrent, device density, thermoelectric. That I will show you later on. But these are only for specific material properties. So once you will, let's suppose you want to calculate the band structure, you can select this band structure. If you want to select the effective potential, you can select the effective potential. If you want to select the transmission channel, eigenstates, then you have to select these. And if you want to select the modulus, you can select like that. So whatever property out of these all, if you will get select all, it may take some time. If you want to only require few of them out of all, you want to calculate these out of all the property. So this is band structure, effective potential, transmission channel, eigenstate, modulus, and even potential, so effective Harty potential, exchange correlation potential, neutral atomic potentials. Even van der Waal interaction is also possible. You can include this van der Waal interaction to calculate the modulus. It can calculate. This is Berlin-Jones root point. You can see the Berlin-Jones root point is there. You can define according to your particular Berlin-Jones high K symmetry, high symmetry K points in the Berlin-Jones. You can define. You can add or delete particular point and change these points manually. And then you can click on this generate file option. You can see here the calculation is finished for this particular main input file. So main input file SCF calculation is finished, which took around 40 seconds for this particular unit cell, particular atoms. Now we have to do the analysis of these all input file. So you can see here, I have to run these also. I will right click on this band structure and click on run button. I will right click on this effective potential and click on run button. I will right click on this transmission channel and click on run button. I will put it my all input file to run condition so that it will run the job and it can plot it. So I'm running here. My all calculation is running. You can see here in the bottom of the page. You can see the calculation that is completed, it's running, and rest of them automatically it is executing. Once this running calculation is completed, the next queue will start running and then next will start automatically executing, so that we have not to wait for until finish then start. It will execute it like that. It is showing the calculation finished. Whatever time it is there, it will show it like that. Now parallelly, the output file is generating that you can see here in this slide. As I told you in the beginning, this is our input and output file area, location of the input and output file. Bottom of that, this is property of particular crystal or device or material, whatever selected. That particular coordinate, number of atom and lattice will be displayed. If you would like to visualize the output, you can click on this particular XML file, right click and click on show view. Now you can see here the band structure is plotted. This is band structure. If you want to zoom on particular location, you can right click and draw the rectangle so that it can zoom, and you can find the direct band gap on particular Brilliant zones path, that you can also find it out. You can click on home so that it will become, and if you will click here on this export button, let's suppose you want to export this data, you can click on this export button. You can save wherever you want to save your output raw data. You can click on this image, JPG, BMP, PDF, TIFF, EPS, text file, whatever the file format you want to save, click on it and click on save button. It will save your data on that particular locations. Now, this is for band structure. If you want to see a transmission channel, you can right click on this transmission channel, number of channels with the minimum -10 electron volt to +10 electron volt energy range. This is transmission channel. If you would like to see the eigenstate, just right click and click on show view. This is for eigenstate for this particular crystals. Band gap value will be displayed. This is 3-dimensional plot. If you want to see in x by xz, by z, by x, zx, whatever the planes you want to visualize your output, it can be visualized. And click on this 2D. If you want to see the 2D plot along the x-axis, along the y-axis or z-axis. This is along z-axis. If you want to see this different color mapping is also there. This is plane display. If you want to see the stereoscopic display analysis, this is stereoscopic display for this 2D, 2-dimensional results. So whatever this particular format you want to do the study, so 3-dimensional plot, 2-dimensional plot or 1-dimensional plot, it can generate your output. So this is different output. The software can generate it in 3D, 2D and 1D. And you can also export your data by clicking on this export button. In this particular format, text also, you can export it. Now, you can see rest of the calculation are running it. The calculation is running the job. And modulus and other properties will be calculated in the MATLAB. So if you want to see this effective potential, you can right click, and this is for effective potentials. Effective potential with the particular isosurface. You can also enable the blending and change the surface things. These ISO values. And if you want to see the 2D output in any of the planes, it will generate the 2D results as well. And 1-dimensional graph. So this is simple. I have taken the simple structure and done the job and calculate the properties. Some other property, if you will right click here and go to the open containing folder. This is a particular project where we have run the job. So in this, not only a device studio output, there are some output which is generated in MATLAB format. As you can see, the elastic modulus, eigenstates, effective potential, calculated band structure. These are MATLAB files. So some of the file can also be seen in the MATLAB, like total energy. So this is total energy transmission channel. XML file is generated and MATLAB file is also generated. So if total energy you want to see, you can see in the MATLAB format. As you can see, I have this MATLAB. So I can browse particular folder in the MATLAB. Go to this particular folder. And here, if you want to see the total energy, this is total energy value. If you want to see the eigenstates, this is Fermi energy, number of bands, refractive index, or if you want to see the modulus, elastic modulus, you can load the file and click on data. It will share the Young modulus, data dot Young modulus. Like it is generated the Young modulus data. Similarly, some stiffness or the shear modulus or Poisson ratio, that is also generated. It is generated the data for shear modulus as well. Similarly, whatever the data is you want to plot, it can be integrated with MATLAB as well. So this is simple structure which I took and try to show you. Now there are a couple of other options is also there in the builder tool. You can see I this minimize it section. Now here you can see there is a builder option is there. This builder option will help you to build the structures, molecule 2D, decomposition, devices, convert to devices, interface builder, fill junction, CAD atomic, redefine crystal, surface layer, symmetry, standardization, graphene nanoribbon, graphene nanotube. Grain boundary will be enabled once we will make the surface. Similarly, nanowire will also be enabled once we will make the surface. Disordered, if any other file extension, you can also convert. So click on the surface and here we can make it the surface plane. So we can define this unit cell to make the surface slab. We can cleave the plane 100, 110 plane. This is 110 plane. This is 111 plane. This is 011 plane. This is 001 plane. So whatever the plane you want to define the surface, that you can define it according to your particular needs. So let's suppose you want to make it 100, you can make it 100, and these are all silicon coordinate point that is automatically generated. Vacuum, if you want to create the vacuum, you can create the vacuum. If you want to define some slab, you can also add the vacuum thickness or slab thickness like that. The slab thickness can be increased. You can create the slab as well. If you want to add the vacuum can be the vacuum can also be added. And if you will decrease it, you can decrease the thickness of your this particular slab. And vacuum can also be reduced in the unit cells. Okay. and click on build button. Now this is your surface lab at 100 plane. And now if you want to simulate this structure, similarly follow the same procedure and you can get it simulate. And if you want to work on other, let's suppose you want to work the same material, this crystal you want to redefine, you can go to the build option and click on this redefine crystal. Once you click on this redefine crystal, there is a option where you can define your, again, manipulate your crystal lattice. So there is A, B, C. There are three dimensions: A, B, and C. C is vertically, B is horizontally, and A G direction. If you want to repeat the same unit cell, let's suppose 4 times in A direction, you can click on it. The G direction, that is called Z direction, 4 times is repeated. If you want to repeat in C direction vertically 3 times, you can mention it. The 3 times vertically direction, it will be added. If 4 times you will change it or 5 times, you can change it and click on this view. And then you can click on build option. It will become the lattice. So this is manipulation. If you want to zoom it, there is a zoom option where you can zoom your unit cell. Now you can see here, this is single layer of silicon atoms. Okay. If you want to add some doping, you want to add some defect, you want to create some defect in this particular structure, you can click on this particular atom, select the particular atom. So, but defect, there are multiple way where you can create the defect. You can select particular atom and press this delete button. There are delete option on the top. You can select it and delete it. That will create the defect in your sheets. This is one procedure. You can also undo it if anything by mistake happen. You can undo it. If you will select, you can also draw the rectangle. Let's suppose if you want to select a particular location. You can also draw the rectangle like that. So what you can do, you can zoom particular regions and then click on the select options. If you want to draw the rectangle, you can draw the rectangle. That number of atoms, whenever you will maximize, you can select it and press the delete button. That particular location will be deleted. It will create the defect. If you want to replace the atom with the N type or P type to create the defect, you can select particular atom, and this is another option near to the delete option. There is option called delete replace atom. So I can select this replace atom. Here you can see the periodic table as open. From the periodic table, what type of element you want to dope in your particular sheet. I am taking an example. Your particular problem may be different, but you have to create, since the license is already given for 1 month. So the problem you can work in your particular system. We will provide the documentation, video, tutorials, and help later on as well. So the periodic table will open once you click on this replace button. Now, if you want to replace this silicon atom with the magnesium, you can select this magnesium from periodic table and choose OK. Now, the color of the atom is also changed so that you can identify that which atom were doped by you. So it will become changed. And if any bonding is changed between the atom, then you can draw the rectangle to select all the atom and click on this recalculate linker bond. Right side top, there is option called recalculate linker bond, which will basically the between two atom, the bonding will be calculated. Maybe the mismatching will be there or bond is not properly aligned, that magnesium with the silicon atom, then it will automatically fetch the bonding if anything missing. So you can always click on it, and based on this introducing the defect, what will be the property of your material or devices, that study can be performed. Now, if you will go there You can see on the top there are multiple other options is there. These all options will help you to build whatever kind of structure you want to create. Now we can run the simulation. So I will go to the NanoDCAL simulator and click on SCF calculations. I will follow the same procedure. I will click on generate the file. It has generated my new SCF input file with this redefined crystal. So I will run this job, right click and click on run button. So the calculation will run here. It will show. In the meantime, I can select the analysis also. So I can go to the analysis option where whatever total energy or charge, Hessian, electron density, potential I want to plot, I can select that particular features. I can, since the number of atom has been increased, so I will take only few particular options, analysis option, and click on generate file because it may take some time. So I will parallelly put it on the run to all my input file. I will right click simply and click on run button. Right click simply and click on run button. Right click and click on run button. Now the calculation in the bottom of this C, you can see the calculation is running. Now this builder that you can see here, this will help you a lot for building molecule decomposition devices. You can also convert your material to device to define some electrode. You can also bend. This feature will be enabled once you will created your device. Interface between two different material can also be created. You can also fill your junction with the CAD atomic position. You can see this surface slab, symmetry, graphene, nanoribbon, grain boundary. So the calculation is running. In the meantime, if you would like to build some different kind of other structures, then you can go to this graphene nanoribbon. This is graphene nanoribbon. Define the unit cell of nanoribbon by the chiral vectors. So by default, carbon elements are there. But if you want to take it different other material, just click on it. The periodic table will open. From there, you want to make it boron based or any other material based. Select it according to your convenience. Bond length between two atom, carbon-carbon atom can be defined. This is a passivation dangling bond with a hydrogen atom. Let's suppose you want to protect your seed with the hydrogen atom. You can passivate with the dangling bond and you can define this chiral vector n and m value to create a nanoribbon. So this is like I have can see the preview before I build it. So I can create this type of nanoribbon like that and click on build button. So simulation is running. So let's wait for 1 minute. And similarly, in this particular sheet, if you want to add the doping, you can add the doping and other things. For that purpose, do the same procedure. You can draw the rectangle. Let's suppose this hexagonal, this particular hexagonal you want to delete. So select on only that particular area. It is now selected and press the delete button. It will be deleted. If you want to move it, there is movement called rotation. Either you can move the atom on plus x, plus y, minus x, minus y, plus z, minus z. With particular distance, you can move particular atoms. or if you want to rotate it, there rotation is also there, clockwise, anti-clockwise, with whatever degree angle you want to rotate, 30-degree angle or 40-degree angle, you can rotate the structures or particular atom on particular angles, anti-clockwise or clockwise, in any direction. So the rotation will become is also possible. If you want to interact the ion with this particular seeds, so what you can do, there is option called add button. This plus option is there. Once you click on this plus option, the periodic table will open. From there, you can see there are a lot of options are there. If you want to add the lithium, you can select this lithium option. You want to interact with the seed and click on OK. Now here you want to, let's suppose, add the lithium here. So lithium is added in this particular location. I can see in this left property bar the coordinate point and the elemental name. So this is a lithium. If you want to change here, you can also change it. So this lithium atom is there. If you want to change this location, you want to move it. So you can move on particular position. So you can see this is moved on top. And if you want to add more atom with that, that can also become added. And I will try to create the another mirror of the structures. So for that purpose, I will just select the layer. I will draw the rectangle so that my layer will be selected. You can see the layer is selected. If I want to make it the mirror of the same and want to sandwich this lithium atom in between two atom, so what I can do, there is option called mirror atom. So I can mirror the same seat, create the similar kind of seat in XYZ normal vector with a distance of let's suppose 2 angstrom. I can apply, but it is basically moved in right directions. So what I can do, I can just this is two particular seats parallelly. Okay. Now I have to change the position of this one, this out of the lattice. So what I can do, I can select it. I can hold the left mouse and draw the rectangle to select, and then I will move its position. So let's suppose I will move on plus by direction. So it will move 3 times. I have moved, and then I will move it. I will click on move. I will move in minus z so that inside of this lattice I can fit it. Now I can zoom this particular unit cell that you can see here. The bonding between all these atoms has been disbalanced. So for that purpose, what I will do, I will select all and click on this recalculate linker bond. Once it is done, now you can see the all bonding is proper and it's ready. The lithium ion in between. This is one simple dummy example type of things that I created so that whatever the manipulation, whatever the desired shape you would like to create according to your particular research, you can create like that. You can define some electrode also, or you can make more H2O. You can also include with that, or different possible combinations are there. I don't know what problems you are working, but I can ensure you the software can help you a lot to modeling whatever the desired type of structure you want to model and simulate. So this is different angle. I can view in X by plane or by Z plane, whatever the plane you want. The simulation is running that you can see. So since whenever the number of atoms will increases, the simulation time will increases. It depends on the system, the computer which you have, how much configuration of your system, as well as the license of the software. So your particular license will works on single core. It may take some time, definitely, because it is a free trial. Whenever you will purchase, we can try to provide you the parallel license so that you will get the faster speed. Now it is running it. In the meantime, I would like to show you some other type of structure that we can create. So I will go to the file option and import local button and go to this 3D material. Go to the conductor, pure metal. Let's suppose I want to work on silver. So I selected this silver element. Next element I can import, that is called as example I can open gold. These two material, but whatever convenient for you, you can load your convenient material. If in the same lattice, same type of like a hexagonal type or FCC type, the lattice types would be same, then you can try to make the heterostructures. So go to this build option and click on interface builders. This new window will pop up where you can select the particular element and then particular new element. So I have selected silver and gold, and this is a grid size, scan angle, rotation, strain I can apply on the first surface, strain on second surface or on the both the surface. Click on match. You can see the lattice matching, lattice mismatching on particular number of atoms or mean absolute strain on this particular points. So this particular point, the red one is indicated, and click on preview. This will see like that the interface on this particular point. Silver and gold interface is there. If you want to see on this particular point, you can see the total atom numbers, angles, rotation, mismatch percentage, lattice area, strain U, strain B, strain theta, and see the preview. This is preview at this particular number of atoms and mean absolute strain. So heterostructure interface will be created like that. Click on build. Once it is ready, click on build button. Now it will be ready here. Proper, it is done. And then you can simulate this kind of heterostructures also. For the simulation purpose, just do the same procedure, simulator, NanoDCAL, and then SCF calculations. You can also relax your structure. So this is for relaxation, where you can relax by using the molecular dynamics or conjugated gradients. So you can optimize your structures also. Iteration control, same parameters are there. If more than 3 materials are there, you want to make the interface of more than 3 material, then there is option called fill junction with CAD atomics. Or here there is option called CAD2 atomic. In the Cat 2 atomic, there is option called you can draw the rectangle. There is another option you can draw this another material. This is another material that you can see it, and other four material. These are, let's suppose, different material. You can right click and set the materials. From here, let's suppose you have selected the silver and then OK. This is the next element. You can set the material. Browse from the library. Let's suppose arsenide. You select it. Then this is the third element. You can draw it, select it, and if you selected the, let's suppose AU, then next element, if this is another element, you can set it and go there and find other element which you want to align with that. Let's suppose you want to take this arsenide again or aluminum, whatever. Select it. All materials are ready. Go to the calculation and see the preview. You can see the interface between four material can be created like that. So these are four different material that I created, and click on build button. If there is any mismatching, you have to properly mismatch, or you have to align it. You have to change its positions. So that is possible. You can change its, the location, like you can hold the left mouse and move its position. So you can move like let me move it. So we have moved it. Now select all and make it this linker bond. Still, if it is not bonding, these particular remaining things, we have to move it. Hold the control button and draw the rectangle. And then move. And draw the rectangle and click on move. So by this way, you can make four material interface like that. It can be connected in this particular manners. Some manipulations need to be done. Whatever the desired things you want to create, it can be done in the same manners. So software will be very broad and a lot of things are there which you can do it. And in the meantime, if you want to create the material till now, that whatever I have shown you, that I imported from the library. If the material is not present in the library, then you can do one thing. Go to the file option, go to the new option and click on crystal. Once you click on crystal, this new window will open where you can see you have to define the lattice parameters. Lattice space group 1p1, 2p1, 3p2, 4p21, 5c2, 6pm. These are all space group. So accordingly, the space group, the Brevis lattice will be selected, which may be orthorhombic, base centered, or which could be a tetragonal body centered, and A and C or ABC will be enabled as per the requirements. This is all fractional coordinate points. You can enable the coordinate point. By default, element is carbon, but if you want to make it NaCl or any other element, you can create easily. Let's suppose you want to create NaCl, you can select this Na. If you want to make it Cl, So whatever element you want to choose, you can choose like that. And this point should be different because these are coordinate point, and click on preview. Conventional cell, primitive cells. So based on the selected particular features, you have to like enable this particular things. It will display. So this new material can be created here. So you can click on this create crystal or click on this new material. You can create like that. This is all crystals. Conventional cells and primitive cells. Both can be created by yourself also directly here. And you can see the symmetry operator x by z minus x minus y minus z, or the all the symmetry operator space group information that is auto generated. And click on build button. So the new crystal can be built like that. There are two NaCl crystals are there in this. If you want to delete one of them, you can simply select that particular crystal type. It will select like that and press the delete. And then if you want to redefine the crystal, go to this redefine in the build option, redefine option. You can redefine this crystal position. So this is an example I'm taking it. Maybe your particular structure could be the different one, but how the procedure will work that I'm telling you. And if you want to import other format, let me show you. Let's suppose you have a CIF format. So what I will do, I will go to my desktop where some of the file may be present. There are two file CIF format is already available in my directory. So this is one gallium arsenide and MOS2. So if you want to see a gallium arsenide, .cif extension is the file extension. I select and load it. It will become load in my dashboard. So this is my gallium arsenide file. Similarly, if you want to load other format, there is MOS2 file in the same. So this is MOS2 file that I have loaded. So from material project open source library, you can download and you can import. If you want to delete undesired, you can simply delete it. There is option called build and convert a file option. If you want have other file extension, go to the browse. In the same folder, there is some different Python file is also there. Python source file. Python silicon, I can select and open it. And I have to convert this ATK PY file to HZW file first, either HZW or XYZ. Once I will convert in these extension, then I can upload it. The ATK PY file can also convert and upload. So I converted in XYHZW, or I can also convert in XYZ. Translate file success in this particular folder, and then I can load the other file extension if you already working. So you can try by yourself if your particular existing material can work directly. Now you can see earlier there was only gallium arsenide or MOS2 file present. Now this interface HZW and XYZ both file are there. So I can select it and click on open. Now it is loaded. This file has been loaded in our. So I would like to check the chat box for a few minutes, and then there will be a one session on the experimentalist part, which will be delivered by one of the professor from Pandit Deendayal Upadhyay University, Gandhinagar. So if somebody file is that software is closing, it may be a graphics card problem. So you have to check your computers. So your particular problem, basically you have to it, or individually we can work together. We can individually work together. And in the meantime, I would like to show you a lot of other video that we already prepared on different problems. So I can show you here. This is our YouTube channel, which you can type Impulse Technology Innovate Your Research. In this Impulse Technology Innovate Your Research, you can find these are all video on different problems. We have built it. So you can become familiar with the software by following this video, which is openly available for everyone. You can simply type Impulse Tech Innovate Your Research in your YouTube channel. So this is was for help purpose. Apart from that, I would like to tell you the help as well. This is nanoacademic.com parent company, where you can go to the bottom of the page and documentation page. In this, there is a nanoacademic.com NanoDCAL and go to the tutorial. In these tutorials, some of the tutorials are present related to photodetectors, ozone thermoelectric property, 2D material, spin, molecular electronics. These are all tutorials are present on different applications. And I would like, if somebody works on experimental part, I would like to tell you these one of the information about the experimentalist purpose. So there will be a half an hour session will be delivered by one of the professor from Pandit Deendayal Upadhyay University, Gandhinagar, Ahmedabad. He will show a small presentation related to experimental how the simulation tool or experimental can work. So those who want to synthesize their materials, we provide this micro probe stations related to thin film applications and solar cells applications. So if you have some sample, this is experimental sample holder, micro probe stations, and this is a light source and a vacuum source meter. We can also provide. We can provide you the chillers also for cooling the sample, and this light intensity can also be fall. And this probe station is basically a compatible with vacuum. Inert gas can also be controlled. Out gas, inert purge gas will be possible from minus 30 degree to 200 degree centigrade temperature. We can study the sample characteristics, IV measurement, and all those things. So there will be a half an hour session on this probe station related application, which will be delivered by one of the professor, Dr. Manoj Singh from PDPU Gandhinagar. So kindly wait for 2 minutes. And in the meantime, let me check your questions. So Raman property is also possible. Transport property is also possible. So any Windows system, the software can work. Either Windows 10, 8, 7, the software can work easily. But 32-bit is not usually supported. So basically, the calculation time is dependent on the computer and the license, because this license is basically the trial version and it is restricted in terms of speed. So simulation speed you will not get faster. You will get all the features and you require good systems also. And time dependent on the particular features, the key point sampling, iteration, and many more things. So as I already showed you, the nanoribbon can be drawn and you can build it easily. Optical property calculation and Raman property calculation. There is some video. Even I can show you in the second parts also. You can see this is a left side optical property and Raman property. These two video, once you will watch it, you can calculate it. So I can share you in the chat box of this link, Raman and optical, so that you can also check it. So you have to measure the direct or indirect band gap by drawing the lines, or MATLAB. It will generate some output in the .mat extensions. In the MATLAB also you can get some direct or indirect band gap. If you are unable to open the surface slab, just select that particular material, and that material should be loaded in the back side of this screen. So as you can see here in this particular screen is there. If the material is selected in this black screen, then the surface slab option will be enabled. Raman property and transport property, it is already there. You can see this is for thermoelectric, Phonen thermoelectric transport property. Tutorial is there. We can also show you. So basically theoretical part you have to learn it. I can tell you the application of the tool. So minimum like 8 GB RAM, i7 processor will be better. Otherwise you will not get the speed faster. Raman property is possible. I already shared you the video. Even in the from the second session, we can also try to cover up some property. Those who have getting some Q sub error, there may be some problem in the system. We can look it to the later on. MOS2 structure is possible. You can get from the library also. So if you do not get the license file, I can share you by email or WhatsApp. You can contact us, or WhatsApp you can contact. Price I can tell you, it dependent on the number of licenses and validity. 1 license, 2 license, 5 license, 1 year, 3 year, 5 year. So dependent on validity and number of license, the price will be vary. Optimization is possible. Electrode is also possible, that we can discuss in the second half, where we can define some electrode and transistor. In second session we will discuss. So if software is closing, it means there is some system problem. License cost depend on that, as I told you, the validity and number of license. So let's share my screen or the PPT parts. So one of the professor from PDPU Gandhinagar, he will deliver the rest of the session on experimental and synthesis parts of the material characterization on probe stations. So I would like to share the screen. Just a minute. So here one of our that Dr. Manoj Kumar is there from PDPU Gandhinagar, and he will deliver half an hour session on advanced characterization synthesis on LASC product. Dr. Manoj, can you hear us?
Hello, are you hearing me?
Your voice
Hello.
is not properly. So can you please speak loudly?
आपको मेरी आवाज अब आ रही है?
Yes, yes, we can hear you.
Okay. Now you can open the slides. Slide number first. I am Dr. Manoj Kumar, PhD IIT Delhi, and now currently working as an associate professor in Department of Physics, PDEU Gandhinagar, and I am also running a company, Laboratory of Advanced Synthesis and Characterization. First, I will give you the brief. Please go to the second. This slide. Thank you. Brief overview of electrical characterization techniques. Generally, in electrical characterization, we do resistivity measurement, dielectric measurement, and impedance spectroscopy. In resistivity measurement, commonly used to characterize semiconductor material and thin films. So in resistivity measurement, there are two techniques. One is 2-probe method and other is 4-probe method. So most of the high resistivity sample are generally done by 2-probe method, and having a low resistivity is generally done by 4-probe method. Now, after that, we have dielectric characterization, in which we measure the capacitance, dielectric constant, and dielectric strength of the material. In this also, we are generally using 2-probe method. After that, we have impedance spectroscopy. Impedance spectroscopy provides insight into the material properties, including charge, transport, and relaxation phenomena, widely used in research, development, and quality control of the electronic component. So you can also see the image. In first case, we are seeing 2-probe. So voltage and current is measured by the same probe. And in second image, we are seeing the 4-probe, where current is delivered from outer one probes and voltage is measured from the inner one probe. That means that current and voltage are measured separately. That is called 4-probe. And most of the semiconductor characterization is done by using 4-probe method. This 4-probe method can give me the information about the resistivity, and we can correlate that resistivity with the doping constant. Doping density, sorry. Okay. And most of the time, we generally try to find out the surface resistivity. Sometimes our sample is not having defined geometry. That means that we do not have any idea about the thickness, or our thickness is not uniform, or shape of our sample is not square or circle. At that time also, we are going to use that 4-probe method, where we call it Van der Pau method. This method is also used for Hall effect measurement, 4-probe or 2-probe method. Now, after that, our system is generally designed for solar cell characterization that can also be used for other electrical characterization. In solar cell characterization, we generally do first current voltage characterization, measure the current voltage characteristics of a solar cell under different illumination condition. Illumination means sun condition. Most of the time, we generally characterize our solar cell under one sun condition. One sun condition means that 1000 watt per meter square at 25 degrees Celsius. Now this provide me information about open circuit voltage, ISC, fill factor, maximum power point. And we can correlate the values of VOC, ISC, fill factor, and Pmax with the material property of that sample, you can say. Crucial for evaluating solar cell performance and determining parameter like efficiency and series resistance. Because like efficiency, most of the solar cell we generally find in our market is 20% efficient silicon solar cell. Okay. And in our laboratory, if we are making perovskite solar cell, they can have a efficiency of 16%, some 18% or 20%. And internationally, they are making a solar cell in the range of 24% perovskite solar cell. After that, there is solar cell characterization called spectral response. That means that measure the electrical response of a solar cell as a function of incident light wavelength. As all of you know about that, we are generally focused in visible range. Visible range lies from 400 nanometer to 800 nanometer. So all the solar cells are planned to maximize plan to use the this optical range from 400 to 800 nanometer. So this is showing you the spectral response. That means that number of electron hole pair generated at certain wavelength and their collection probability. So by seeing this graph, we can predict that recombination time is high, or what is happening at the interface of metal, semiconductor, etc. So provide information on the cell ability to convert light of different wavelengths into the electrical current. Now, this also enables the assessment of a material quality, junction properties, and potential performance enhancement. If you look at that conversion probability of a 400 nanometer wavelength is 0.1 as compared to that 901. This is the spectral response of solar cell. That means that whatever UV light you are getting at the surface of your silicon solar cell, that uh, that generate electron hole pair, but these electron hole pairs are you can say recombine at the surface, so they are not collected by the electrode. That's why we have this response. Similarly, as we go further, so response increases, and after that it also decreases depending upon the band gap of the semiconductor. Okay, after that we generally do solar cell characterization, that is called impedance spectroscopy. And you can say that we have published approximately 30 to I think 40 papers we have published in impedance spectroscopy of silicon solar cell, dye-sensitized solar cell, perovskite solar cell, etc. And that is very specialized technique that give me the information about the interface property. All of you know about that. Solar cell is a PN junction device. So a PN junction is making an interface. So by studying this impedance spectroscopy, we can find out what is happening at that interface. And in solar cell like that, we have a silicon solar cell. So on back side, you have P plus. On front side, you have N plus N junction. N plus and P plus means that highly doped, 10 raised power 19 to 10 raised power 20 doping per centimeter cube. So this is very sensitive technique. It can give you information about these junctions also. We have published certain paper where we discuss the interface at the junction on back side of the solar cell, like P. P is our base, and on back side we have P plus. So P plus junction can also be find out this impedance spectroscopy. Analyze the electrical response of solar cell over a range of frequency, provide insight into the charge carrier recombination, transport processes, and interface properties, help identify factor limiting solar cell efficiencies, and suggest strategies for improvement. So we have taken 4 cells from a silicon solar cell manufacturing line, and we have analyzed that solar cell, that why there is a difference in the efficiency of solar cell from the single line. This technique is very helpful there. After that, we can have that solar cell characterization, thermal characterization. That means that effect of temperature on the characteristics. In that, we can also characterize their IV characteristics, their spectral response, and their impedance spectroscopy with respect to temperature. By doing this, we can find out the activation energy of different effects present inside the material. So in thermal characterization, generally evaluate the electrical properties of material as a function of temperature, help understand how temperature affect conductivity, resistivity, and other electrical property. This is important for designing a reliable electronic devices for various operating conditions. That means that, let's say that we are making a silicon solar cell, okay, and it is showing 18% efficiency in standard test conditions. Standard test condition means that 1000 watt per meter square at 25 degrees Celsius. Now we are planning to use this solar cell in Rajasthan or some very hot climatic condition. So by studying their thermal characterization, we can predict that how much solar energy this type of solar cell are going to generate, and what will be the cost of average cost of solar energy generated by this plant, because efficiency decreases with increase in temperature. But as you know that in Rajasthan, Gujarat, etc., the sun energy, or you can say solar illumination, is high. So we can find out this. After that, we have solar cell characterization, light soaking and degradation. So silicon solar cells are very stable, but the solar cell we generally fabricate in our laboratory for research purposes, like dye-sensitized solar cell, or perovskite solar cell, or heterojunction of perovskite and silicon solar cell. They need to be tested for their stability in temperature and light condition. So in this light soaking degradation, what we generally do, we evaluate the long-term stability and performance degradation of solar cell under continuous illumination, help assess the reliability and durability of solar cell material and structures, important for understanding the aging mechanism and optimizing solar cell lifetime. That means that by studying this, we can uh, uh, we can understand various mechanisms responsible for the change in the IV characteristics of the solar cell with time, with light, with temperature. These characterizations are done, can be done in our system, and our system can also do all the electrical measurement characteristics of semiconductor and dielectric material. Now, I would like to introduce our 2-probe or 4-probe optoelectronic system. We call it optoelectronics. That means that we can illuminate our sample in this. We can change the temperature of the sample in this case, and we can do 2-probe and 4-probe measurement of our semiconductor or dielectric materials. So, if you look at the specification, we have two 4-probe internal probes with 4 standard tungsten electrodes for making electrical contacts, and we provide customized connection like BNC or Tri-X depending upon the requirement of the customer. People working with biological, they generally require banana plug. So we customize that. We provide banana at the outer end for them. In this system is also vacuum compatible. That means that you can create a vacuum in the system, and if you wanted to introduce certain gases to create certain environment, you can also do. Vacuum compatible as a single piece chamber. Approximate diameter of this chamber is 220 mm and thickness is approximately 60 mm. And we have a chamber lid here. Chamber lid is having a generally 45 mm dia standard quartz window. Extra add-on, what we generally provide, we provide temperature range from room temperature to 350 degrees Celsius with PID control. And when we take at low temperature, most of the time for perovskite and dye-sensitized or some heterojunction solar cell, we can also generally provide temperature range from minus 30 degrees Celsius to 120 degrees Celsius, because most of the solar cells are characterized in this range. Sample area we generally provide from 25 mm to 45 mm into 45 mm. Accuracy is from 0.1% of the temperature. And with that, we also provide LEDs for spectral response. We generally provide cool white LED rating approximately this for one sun condition. That means that we characterize that LED in our standard system, and we provide a reference solar cell so that we can calibrate our LEDs. Okay, customized contact, microwave compatible. This system can also be customized for using in gas sensing purpose. This is our 4-probe optoelectronic probe station. In that, we provide probes that can be adjusted from outside without disturbing gas or vacuum environment. So in that, we can provide 4 probes. If someone need only 2 probes, we can also provide 2 probes only. All features are same from the previous one, but only difference is that now we are controlling the position of X, Y, Z from outside without disturbing any vacuum, any gas environment. This is very important when we are doing an electrical characterization of some samples. Let's say that there are 5 to 10 dots over that sample and 1 dot gets filled. Okay, at that time, if we need to change the dot, then this type of system will help us that without disturbing the vacuum and the gas environment from outside, we can change the position of electrode. Okay, so chamber lead temperature range is also same for this system. Room temperature to 300 degrees Celsius, PID controlled. Minus 30 degrees Celsius to 120 degrees Celsius, accuracy 0.1 degrees Celsius. LEDs are also same. After that, we provide one system, smart UV visible. So this system generally use UV visible temperature range from minus 20 degrees Celsius to 100 degrees Celsius. That means that you can do UV visible study of your thin film or your liquid sample from minus 20 degree Celsius to 100 degrees Celsius. In this, we can do in situ electrochemical UV visible temperature is possible. Absorbance in time domain analysis with temperature is also possible here. There is one more thing you can see, you are seeing on your right hand side. That is our sample holder. So this is perovskite solar cell LED sample holder. So in that we can characterize perovskite solar cell where we need back contact. We can also characterize LEDs or JFETs, semiconductors having back contact. And in that we generally characterize 6 samples in a single go. Repeatable result, easy sample holding, 6 pixels can be analyzed by using rotating switch. This is our optoelectronic probe station we supplied. Okay. This is our new probe station we are designing for a institute. Here we are combining the property of both 2 probe system and the back contact system. Hello. So all the conditions are same. You can create vacuum, you can create gas environment, you can create stability studies. This back contact is generally used for stability studies. That means that you have prepared a sample of perovskite solar cell and you wanted to study how this solar cell is going to behave after, let's say, 10 days or 100 hours of sunlight illumination, 1000 hours of sunlight illumination. So at that time, we generally put our solar cell in back contact mode, that green you are seeing. Ravi ji, next slide kar dijiye. Next slide. Ravi ji. Hello.
Yes, sir. Yes, sir.
Okay, आपको मेरी आवाज अच्छे से आ रही है?
Yes, we can hear you, sir.
Okay. हाँ. ये आप नेक्स्ट स्लाइड करिए एक बार. हाँ, yes. Okay. In this system, we are supplying this system to ISR Kolkata, and we have combined our stability setup and 2 probe system. So somewhere in laboratory, we generally find a lot of problems in characterizing our samples. Let's say that I am making a thin film. Okay. and I wanted to characterize that. If I have taken a stability setup, at that time it became very difficult to characterize that. If I have taken that 2-probe or 4-probe system, at that time I can do that. But let's say that I am making a solar cell also. So this system combines both the things. Stability setup, that is green one, is your stability setup, and this is your 2-probe setup. Most of the solar cell characterization are done in 2-probe setup. If you need, let's say that you are making a thin film of metal and you wanted to do a 4-probe measurement, we can also integrate two more probe in this case if someone required. So this is from my side. Okay, thanks. And let's go to this slide. Okay, let's go to Ravi ji, ये slide पे कर दीजिए 2-probe 4-probe optoelectronic probe station. If our viewer has certain question, we can answer that. Hello.
So participant can ask their queries, please. You can unmute your mic and ask your query directly to the Dr. Manoj Kumar related to this probe station and other product.
Most important part is that we are making it in India and we are customizing this. One of my friend is in IIT Chennai and he has purchased a 4-probe system from outside, and that was not customized according to his need. So now he is going to take one system from our side because we are going to customize the system according to his need.
Sir, I'm having one query. At your
Yes.
lab, only you are designing the probes and supplying it to the users, or users can come your place and do their characterization with
We can
your.
also, yes, user can also visit our laboratory and they can do certain characterization if they need.
Okay. So can you share your number so like whenever required, then we can contact you for the same.
My number is 9825 388 335.
989825.
ये आप ये रवि जी से
So,
ले
हाँ,
लीजिए।
that's what I.
हमारी लेबोरेटरी में हम ऐसे हेल्प करते हैं स्टूडेंट्स की, अगर उसको 1-2 करेक्टराइजेशन करानी है तो हम करते हैं उसके लिए।
अच्छा, सो हम आपसे फिर आप नंबर शेयर करेंगे, राइट?
हाँ, आप रवि जी से बोल दीजिए कि वो कर देगा आपको, लैब का
He will
एड्रेस
share you
वगैरह
the
सब
information.
वो बता
Okay.
देगा।
Sir, one more query. Like here we are doing the actual characterization, and with simulation, how we can do it? I mean, here we are using the applications of DFT for it.
हाँ,
So
आप now देखिए, if you are only using DFT,
yeah,
at that time you are going to find it difficult to publish your result
yes,
because lot of people are doing. But if you integrate some experimental technique with your DFT calculations,
mm-hmm.
let's say that if we are doing certain IV characterization and we are able to match that IV from whatever you are doing theoretically, then the quality of your paper improve very much and it can be published in a very good journal.
Okay. Okay.
And
Thank
now
you, sir.
most of the things are shifting like that. Okay, every journal need theoretical as well as experimental.
Okay.
पहले हम करते थे, जैसे पहले हम बिल्कुल एक्सपेरिमेंट करके भेज देते थे, तो कोई कुछ ही इक्वेशन 1-2 इक्वेशन लिखते थे। अब क्या है कि जो व्यूअर है वो भी चाह रहे हैं कि भाई उसके पीछे जो एक्सपेरिमेंट कर रहे हैं उसके पीछे कुछ थ्योरी है, तो वो उससे ज्यादा अंडरस्टैंडिंग बढ़े। और कोई थ्योरी वाला है वो चाह रहा कि मुझे कुछ एक्सपेरिमेंटल एविडेंस मुझे मिले जिसको मैं इसको कोरिलेट कर पाऊं जो हम ऑब्जर्व कर रहे हैं थ्योरी में। तो ये बड़ा अच्छा है, आजकल थ्योरी और एक्सपेरिमेंटल दोनों ही चल रहे हैं।
Okay. Thank you, sir.
Thank you.
Any other participants have any other queries?
So your instrument pricing is available on your site?
Instrument?
Pricing, because if I need to purchase something, so how we can do it? I mean, is it available on your site or somewhere?
You can contact to Impulse Technology is our partner.
Okay.
So we
Fine.
will share the price information. We can discuss telephonically and understand your requirement.
Okay. Okay. Fine. Thank you.
Okay, thank you.
Any more question? रवि जी और कोई है?
I think there is no query. So thank you very much for giving this presentation.
Thank you very much. Thank you very much for listening me. Thanks again. Have a good day. Thank you. Okay.
Thank you. So participant, we will be back at 2 p.m. once again, and we'll discuss rest of the training session. Thank you.
This is my device studio, that is a graphical user interface of this RESCU software, and this interface will help you to model the structure. You can do some modification, manipulation in your atomic structure. So first I would like to import the aluminum nitride. So you can click on this file option, select this import, and this software have two options to import the material. Either you can import the material from local database that exists inside this software, either you can import the material from online database. So I would like to select this import online. And here you can enter the chemical formula of the material, and then you can click on this search option. So here you can see this is the aluminum nitride with different space group. So as per your need, you can select the aluminum nitride. So I would like to select this aluminum nitride, and then you can click on this add option. So this is the aluminum nitride that I have imported from my online database. And if you want to simulate this structure, so you can click on this simulator, select this rescue, and go to the DFPT. So this is the DFPT calculation, where you can see this is the basic settings. In the task, I have selected optical property calculation, and this is the simmering sigma, and this is the resolution, and this is the escape method, real space, and this is the exchange correlation, LDA, GGA, and this is the K-point sampling. This is the iteration control. Here you can see this is the tolerance, charge density, total energy, and this is the basic settings, and this is the Spintronics application, and this is the optic parameter, where you can see damping factor, field direction. So as per your need, you can select the parameter, and then you can click on this generate file. So once you click on the generate file in the project window, you can see the scf.input file for this aluminum nitride has been generated. And this is the dielectric.input file, and this is the Phonen.input file, and this is the optical.input file. So you can select this scf.input file, right click, select this open with, and this is the script for this aluminum nitride. So again, you can select this dielectric.input file, right click, select this open with, and this is the dielectric input file. So first you need to run the scf.input file. So you can click on this scf.input file, right click, select this run option. And if you want to run this job on parallel, suppose 5 core, 10 core, 15 core, so there is no limitation of core, you can define up to 128 core. Then you can click on this run option to run this job. So in the job manager, you can see the scf.input file is in the running condition. So in the meantime, you can select this dielectric.input file, right click, select this run option to run this job. Similarly, you can run this Phonen.input file, and then you can run this optical.input file. So in the job manager, you can see I have run all the input calculation in the queue condition. Like when this dielectric.input file calculation will finish, their Phonen.input file will start automatically. So you can wait till the calculation finished. In the job manager, you can see all the input calculation has been finished. So to plot the graph, you can select this optical.input file, right click, select this open with, and here you can type this command, and then you can click on this save option, and again you can select this optical.input file, right click, select this run option to run this job. So after this calculation finished, their output file will be generated. So in the job manager, you can see all the calculation has been finished, and their output graph has been plotted in the MATLAB. So I would like to open my MATLAB, and from this browse option, you can locate your project into the MATLAB. So here you can see this is my project. You can select, and then you can click on this select folder. Again, you can select this folder, and then you can select this rescue DFPT folder, And here you can see this is the graph. So you can double click on the first graph. So this is the real and imaginary graph of the dielectric permittivity of this aluminum nitride. Again, you can select this folder, and this is the IR intensity of this aluminum nitride. Again, you can select this folder, and this is the photon energy loss of this aluminum nitride. Then you can select this folder, and this is the real and imaginary graph of the refractive index of this aluminum nitride. So thank you for watching the video.
Guess what? 3 hours. In just 3 hours, I learned how to use child.
Hello everyone, myself Deepak Upadhyay from Impulse Technology, Gurgaon, Delhi.
So welcome back to all the participants once again. Kindly wait for 2 5 minute more. Let it join the other participants. Then we'll continue the session. So I hope you have enjoyed the first session today.
Hello, good afternoon, sir.
Yeah, very good afternoon, ma'am.
Please, can you tell me what is the cost of this software? Actually, this is the 1 month license provided by you, na?
Exactly.
So,
So this license is basically the trial version where you can explore the capability and be familiar with this software before going to plan for purchase, so that you can satisfy technically. The pricing concern, it depend on validity. If you will go for permanent, that will cost around 6.5 lakh plus GST.
okay.
6.5 lakh plus GST for permanent license. And then if you go for 1 year, 3 year, other different variations is there. According to the budget and requirement, we have flexible policies.
Okay. If 1 year, if I want to purchase for 1 year.
Around 2 lakh something plus, for 2 lakh
Okay.
near about plus GST.
Okay, thank you.
For MATLAB, some people can create their account on the portal and they can get a student version or some crack version available in the market. From there, you can get the MATLAB. So around 10%, it will be like few of the output can be visualized. In coming version, we are expecting the company is developing some app where there is no dependency on the MATLAB tool. That is under development. So I think we should start the session. So since we already given the license, okay. So many of the people maybe have downloaded or installed their license working. If somebody may have some problem, I don't know it is there because we have tried a lot. If due to your particular computer Whatever the problem is there, we can work out after this session, okay, tomorrow or whenever, and then we can provide you the license. That is not a worry, but you should be evaluated for properly, and you can also circulate or inform your supervisor or your students so that they can check it properly if it is useful for your research. So for research work, you can simply type NanoDCAL, NanoDCAL on Google Scholar, where you can find a lot of papers. Okay, so let me share my screen and would like to continue. Since the license is given, so individual, there are so many people are there in the this training. So individual problem, it is difficult to take it, but we have provided the license, so you can take the particular material that you are doing the research. So it's better to do your research on your particular project or your particular material that you are working on it. So let me continue the session. So welcome back once again, all the participants. Thank you for your good audience and giving your time in first session. I hope you have truly enjoyed it. And I would like to share my screen and we'll continue. The project is like you can use it, but not authorized to publish the papers. Publication paper, you need to purchase the license, but you can use as much as you want. You use, no problem. You can also inform to your colleagues, though you are interested in such kind of domains, to work on it. For internship purpose, you can discuss to us individually. We do not usually, but if we have any requirement for internship, you can call us. We can find out the solution if we have any. So let's get started. Now I will discuss your queries later on. And first of all, I would like to continue my session, my knowledge that I have related to this particular product, so that you will get some insight about the product. So let's continue the session. As you know, the previous session that we finished here, some of the calculation is already finished and the output is generated that we wanted to see it for multiple structures, like multiple atomic structure. As you see, we created this structure and created the defect and run the calculation. It took some time, but definitely the calculation is done and we can see the output. Whatever output we have selected, we can visualize like that, and either in two-dimensional, three-dimensional, or one-dimensional. Similarly, other plots like total electron density and whatever other plot you would like to visualize, it can be done it. Now, many people are working on what I say device applications or Raman properties, optical properties. So I would like to share some video or would like to open some project. So let previously I imported the material from my local library or created the material from scratch. Now this time I would like to import the material from online source. We have an online interface with third-party product, third-party open source library. So once I click on this import online, I will find this window, import from material project. Material project is basically open source library. From there, I can also fetch the material. If I simply type BN, I can find, click on search it. Through the internet, it will search material related to that product. All These are all materials. Whatever I will search it, it will display all the informations. If somebody is working on MGO, simply you can type MGO If it is there, if not there, maybe you have written something mistake, then you can type the exact syntax. If I search here MgO, you can see the related to the magnesium oxide, all materials are present. These are the all material. If you will go for MOH2, I can search it, and this is all MOH2 related materials. If you will search nickel oxide, I can simply type NiO and click on search. It will search the nickel oxide related element. Okay. If I take this VN, I can simply type it, and I can take this. This is cell length, ABC value. This is alpha beta gamma 90 90 90, and this is coordinate point for boron and nitride for this particular structure which you can visualize. So I would like to add in my dashboard. Now it is added here. You can see in this left side as well. If I would like to run the calculations by using this RESCU, that is material simulations. So I go there, either I can perform the SCF calculations. Here you can see the LDA, GGA, PBE, exchange, and other functionals are there, including the hybrid functionals, HSC06, B3lib, Meta GGA, and other functionals is also there. It works on real space and linear combination of atomic orbitals. If you will work on DFPT calculation for Raman and Optical, you can go there and click on DFPT. Now here you can see there is option called task. Phonon band structure, phonon density of state, phonon band structure and density of state, optical properties and Raman property. If I select here, there is iteration control parameter, tolerance, charge density, and DFPT method, Steinheimer and CFSI. This is theoretical things that you have to check it on the Google it. This is basis sets, spin type, and damping factor, incoming photon polarization, outcome photon polarization, incoming photon wavelength, and temperature. You can vary these parameters according to your needs. Click on generate file. It will generate the rescue required input file. You can see the SCF input, dielectric input, phonon input, Raman input, and atomic coordinate point. These are all input file. I can right click and run this input file. So the calculation will start here. So I'm putting all in queue. You can see the simulation is started. It will reflect in this task once the all the loading processing is completed. Similarly, if you will search for other element here, you can search whatever molecule you are looking for it. If it is exist, it will show here. If not exist, you can also draw the molecule here. You can see the molecular builder is there. This molecule 2D. Here you can find this is a molecular builder. You can draw the molecule here. The calculation is all, you can see it is started here and it's going on. Okay. So this was basically a molecular builder where you can build a different molecule structure by clicking on this molecular builder. So benzene or other element molecular structure, if you want to create, this is a builder which you can create here, different type of molecular structures. Let us see the structure of this particular type. So you can see the calculation is still running. It is computing the ion energy and forces, DFPT calculations. Electrical field distributions. The simulation is running. In the meantime, if you want to understand other features of the particular tool, you can see there is a distance measurement. So this top side, if you want to measure the distance of your channel or from one atom to two atom, simply click on this distance measurement tool, then click on one atom, hold the control and click on other atom. In between two atom, if you want to measure the distance, you can see 3.654 angstrom. The distance is measured from center to center, from this particular yellow atom to this particular yellow atom. So this is distance measurement. Similarly, from any atom, that length of channel, length of electrode, or whatever measurement in angstrom you want to do, you can measure it. If you want to see the angle measurement, this is angle. Once you click on this angle and click here, one element, second element, the element. So 3 atom 49.384. The angle is measured. Okay. So angle measurement can be done. Distance measurement can be done. Dihedral can also be measured. So this is dihedral from one plane to another plane. The plane to plane measurement, like in laptop, there is one vertical plane, another one is horizontal plane. So like that, you can measure the distance, angle, plane, and similarly this vector measurement. Vector can also be measured from one to x, y, z coordinate. Vector can be measured, and this is last one for linker bond calculations. So whatever the distance you want to measure of any crystal coordinate point, you can measure the all informations. So if I would like to try to check the output, I can go in my MATLAB, and MATLAB, since all calculation is completed, in MATLAB the dielectric, that Raman properties related things we can calculate. Like that, we can find this Young modulus, Serre modulus, stiffness with this dielectric properties. And that could also be there. Once Phonen calculation done, then we can also visualize the Raman property as shown in the video. if we will try to build the structure, if we will try to make the device structure, then let me try one device as well, and then we'll go for the transistors application. So I would like to import one material. I go to this import local, and from there I want to import one material. Let's me go to the material one, 3D material, and go to this layer material. As example, I want to take one 2D material that's called WSE2. So I will select this material and load in my dashboard. It will become load here. Now, if I want to calculate this material property, I can calculate. I can delete the undesired atom. So I draw this, select this atom and press the delete button. Now I want to rebuild this crystal. So I go to this build option and click on redefine crystal. Here you can see whatever my crystal is. If I want to manipulate my crystal structure, I redefine the crystal positions. So I can redefine my crystal ABC position here, and I can define as per my convenient requires, and click on preview. So this is my structure vertical positions. And click on build. So here this is just a vertical direction. I will click on the alternate coordinate points. I will click on it so I can change its position to vertically. Now this is rotated X by Z directions. So until toward positive direction, I have rotated it. To make the device structure, I will go to the build option and click on convert to device. This is simply a material. It is single vertical layer of WSE2 structures. Okay. Any position we can visualize. To convert this material into the device, I will go to the build option and click on convert to device option. Once I click on convert to device, there are multiple probes are possible. You can see here the left electrode, right electrode, bottom electrode, top electrode, front electrode, back electrode. Up to 6 probe device are possible. In this particular, if you want to decide top and bottom, you can select the top one and bottom one and click on preview. To the angle that vertical horizontal line has been drawn, you can see this horizontal line that will specify the electrode type boundary condition, and this is a thickness of the electrode minus 3.282 or plus 3.282. We can also change this thickness. If you want to increase the thickness of this electrode, you can change the value. The thickness can be increased. And then click on build button. Once you click on it, the electrode are specified. The 2-terminal device is ready, that you can see here on the screen. Now, once the electrode are specified, so that will convert the material into the devices. And we can apply the vicing on top terminal or bottom terminal as per our need. For that purpose, I will go to the simulator. In the simulator, you can see this NanoDCAL is for device calculations. NanoDCAL can also do the materials as well, but RESCU is only for material. As you can see, the device, the material is converted into the device. That's why the device feature is not exist in this RESCU. So I will go to this SCF calculations. Once I will click on this SCF calculation, you can see here the basic setting, electron temperature, energy cutoff, exchange correlation function, LDA, GGA is there, key point sampling, number of sampling point, contour integral is added in this particular device feature, SCF calculation for device, electrode is there, bottom electrode and top electrode. Now this function and contour integral were not available earlier. It is enabled just now. We can define the electron temperature and voltage that we will apply on the terminal. So either you can define 0.1 volt, 0.2 volt, or whatever other voltage on the contact. If you want to apply minus 0.1, minus 0.1 volt can be applied. And then go to the iteration control. Density matrix and Hamiltonian is possible. It will solve the Hamiltonian equations and density matrix. And basis sets is there. If you want to add some doping, you can see the doping function is there. You have to create the doping, either S or W. User defined material need to be created and define where you want to do the doping. In particular area, the dopant you would like to enable. So the dopant area need to be specified. Doping can also be done in particular channel region or something, if you will activate this doping section. And then spin type. With collinear, general spin, type of spin related polarization you want to include, then you have to enable this collinear spin or general spin orbit couplings. And click on generate files. Now you can see the device WSE2 minus redefined. The project has generated where multiple folders are there. Bottom electrode, top electrode, and device. These are 3 folders. Once you will click on that arrow, you can find their input file. And similarly, this is a bottom electrode, SCF input file, and top electrode and SCF input file. So bottom electrode and top electrode, it is distinct. It is separate file will be generated. And device will be the whole complete device, including the electrode as well. So we will run the SCF input file of electrode first. So I will right click and click on the SCF electrode run. Similarly, since the top and bottom electrode both are same material, there is no difference in top and bottom. So either I can take the output file of bottom into the device, or I can take both of them. So let me run both of them or any one. So since I already run the calculation of bottom electrode, which is same material, top and bottom both are same, but the output I can open this file script, device script. So bottom and top both are same, so I can change simply the output of bottom and top are same. So I can mention bottom electrode and top electrode NanoDCAL object.mat file. That will load it. Once the calculation is done, it will load that output file, which can be loaded in this device bar. So that output of electrode will join or integrate in this device SCF input. Then I will run this SCF.input file and click on run button. So simulation you can see it is running and the device one will in queue. That will automatically execute once the electrode input file is finished their calculations. And then go to the simulator, NanoDCAL and analysis part. In the first session, morning session, I introduced you about the material property. I did not introduce about device property. Now this time, I want to introduce about the device property as well. So I will click on this analysis part. Here you can see these are all device property, which does not exist in the morning session that I could not show you. So density of state, effective potential, total energy, scattering state, transmission, photocurrent, IB curve, charge, electron density, potential, conductance, thermoelectric current, Seebeck coefficients. These all are possible. If you would like to calculate, you have to select it. So you can see this is conductance, number of energy band, thermoelectric current with temperature variation. You can also visualize Seebeck coefficient, minimum energy range, maximum energy range with the interval, temperatures, even other IV characteristics that is also possible. Photocurrent for photodetector applications, where you can define the even E0 polarization, linear polarization, left circular polarization, right circular polarization, elliptical polarization, oblique elliptical polarizations. These are all possible with theta, minimum maximum photon energy, key point sampling, and light irradiated region. You can follow the light on that particular directions. The light will fall in photons, and how much light get absorbed, that photon energy can be calculated. So once you will generate the file, it will generate the required input file for this particular session. As you can see, the previous one, the calculation is running, but it may take some time. As you know, the number of atoms are increases. Your license should be in parallel. Your configuration of the system should be in parallel so that you will get the faster speed. Around 72 atom I took it, but it may take time to solve the live problems. So I hope you have seen the device analysis and material analysis. These are all device property. In coming version, maybe other features can also develop. So how the device material was converted? Basically what I did from the beginning, I took this material, redefined this crystal from this bulk to crystal, redefine this crystal position from here. That generated this another material file, this one, and then I can click on here, convert to device, and that makes the device here. And this is called device. If you would like to change the vacuum in your lattice, then you can see there is an option called convert to crystal. In the convert to crystal, you can find here the lattice type: simple cubic, face centered, body centered, rhombohedral, hexagonal, tetragonal, simple body centered, simple cubic, monoclinic, triclinic. And you can add this ABC. Here you can see the vacuum is, if lesser, you can change the vacuum, you can increase the vacuum in the unit cell. To increase the vacuum, just change the cell length. Let's suppose I make it 1.5. So the vacuum in G direction has been increased. If I will change it more, the vacuum can be increased by changing these directions. So not only in A direction, if you want to change in other direction, you can see this is a second Y direction and this is Z direction, third one. So A, B, C, any direction, if you want to introduce the vacuum in your unit cell, you can also introduce the vacuum. You can increase or decrease the vacuum space in your unit cell. If you want to make it this unit cell in the center of this particular unit cell, then you can press this button, this one, center. It will change the position and will be in center of the unit cell. If you would like to add the stretch, you want to stretch the cell, stretch, you want to include some strain, then there is an option called stretch cell. You have to set the stretch factor for each unit cell vector. So either in A, you can apply minus 0.1 stretch. In B also you can apply minus or plus, and C also. Similarly, the alpha, beta, gamma with delta, strain tensors you can apply and you can create it accordingly. And then you can run the job and see the effect. If you want to convert your this you want to remove the unit cell of this particular unit cell, then you can simply press this option, convert to molecule, which will remove the lattice. So I click on it, the lattice has been gone. And if you want to change the bond length in between two atoms, you can select the two atom one by one or draw the rectangle. So the two atom has selected and click on this edit atom with selected option. Where my cursor is, click on it. You will find the Z matrix. In the Z matrix, you can see this is a distance between W and SE. If you want to change the distance in between these two bond length, atom bond length, here you can double click and whatever manipulation you want to change this value, you can change it. So the bond length in between any two element you can change. Even theta angles also you can change. If there is any angle mismatching, you can also change the angles. So this was the device which is going to be simulating. It may take some time. In the meantime, I would like to explore more features. If you would like to bend this device, this is two terminal device simply, where only anode and cathode boundary condition is there. If you want to bend it, you can click on build option and click on bending of device. You can see there is a bending model, one side or both side. So this is initially 30 degree. If you want to make it 40-degree bending, you can see here the bending little bit is done. Your unit cell has become some rotations. If you will change it to 70 degree, it will change that bending of your device. It is specifically for flexible device. If you want to work on it, if you want to change the radius can be changed. So either single side you can bend or both side you can bend like that. And then this bended device, you want to simulate it, you can also simulate this kind of structures where electrode are there in this left side, right side, and angular directions of the device channel regions. This is with bending structures. If you would like to convert into the transistors, there is option called transistors. So this is two terminal device currently, but here for the transistor purpose, click on this transistor option. And for gate region, you can define the dielectric gate permittivity and the thickness of the gates. You can define this gate thickness, gate number of gates, left, right, or top, bottom. This is gate voltage rising 0.1 volt, 0.2 volt, 0.3 volt. Here, this is the gate controlling region. Vertical side, this one which you can see is the region of the gate. And this one, blue region, that is called for thickness, green type. And if you want to change this gate region, you want to increase the gate region, you can increase the gate region value. The gate region has been increased. And this is for transistor, where your transistor may be on the top side or bottom side. But apply some bias voltage, source voltage to plot the IDVD characteristics. Thus, source voltage is also required, VD value. So 0.2, 0.4, 0.6, let's suppose you want to apply. And here you want to apply 0.1, 0.2, 0.3, 0.4, 0.5, like that. We can change these value according to our need. On different devices, we can apply it. And click on generate files. Now you can see there are so many input files generated for the same project. You can see here 0 volt, VD equal to 0 and VG equal to 0. Gate voltage 0, source drain voltage 0. Drain voltage constant, gate voltage is changing. So input file for different devices, the input file project is generated. We have to run all the input file and then do the calculations. And once the simulation finished, then we can do the analysis of our output. Okay. So for that purpose, if you would like to plot the transistors out, you can see this is for transistors plot, analysis plots. Relaxation for device can also be performed. For IDVD characteristics, you can plot the transistors. Now, if you want to, simulation may take a lot of time, but in the meantime, I want to detailed explain about these product capabilities. You can see there is option called BCA, NanoDCAL BCA, Virtual Crystal Approximation. BCA will generate basically the mixture doping, mixture element, the N-type, P-type, compound kind of materials can be created. Where X 1 minus X, the mole fraction, as you can see, the mixture vacancy or mixture atom. So whatever the element you want to create the mixture, you can create the mixture here. LDAPB, and this is composition. When multiple elements are there, you can generate the multiple elements. So silver is there. If you want to add another element, you can see you can add new another elements also. If you want to create other element, you can add these elements and define the composition mole fractions. And it will generate the mole fraction composition file. You can see the virtual crystal approximation with the composition file has generated. So we can create such type of compound materials as well if we required to make mole fractions. So different electrode can be added. You can also add the multiple electrodes. Accuracy, you can find the papers on on Google Scholar. There are so many papers are already exist. You can find these are all recent paper of 2024 by using this tool. So many papers are there. You can simply click and find out. Even more 2023, 2024, all papers are there. So accuracy, since it is there are so many papers are published in good journal, so you can find it very accurate. So you can also use this tool for, I think, a supercapacitor is also possible. Battery related application, it is also possible. That's why we have given you the license as per your need. You can customize and use it. If you want to make the device, there is option called device. Here, if you want to add the electrode, you can see this is a window where left and right, there are two material interface. Left electrode, right electrode. Left electrode, center electrode, and right electrode. Bottom and top, bottom, center, top, front, back, front, center, back. So let's suppose you want to make LCR, left, center, right. Choose it. You can select the left electrode, central material, and right electrode, and find the matching and make the device. By basic procedure, if the material is not aligned, the faces are not similar, then you have to choose a material and make the surface vector. It should be aligned to each other. Surface vector should be aligned so that there should not be any mismatch, and you can create the structure from here. You can see there is a material browse option. Let's suppose I build the material. I take it silver in the left. If I take it as an example, gold on the right side, and on the center region I can take it, let's suppose, the graphene. I can import it and I can see the preview, but we have to match it properly. If mismatching is, see, you can see there is mismatch 50%, but we have to make it this supercell properly. We have to align it or repeat the graphene, create the graphene sheet first, then choose that graphene sheet in the central region, and right region you can choose the different electrode, and left electron you can choose different material, because this is only two atom carbon atom, but proper sheet need to be created first, and then you can make the device here and define the electrode. For graphene related application, let me import one material of the graphene. This is simply a two atom. Go to this redefine and change its positions. You can make it 10 times repeat. It is repeated in vertical, sorry, G direction and A directions. And accordingly, the electrodes should also be the same number of repetitions. To make it proper alignment, the electrodes should also be the same. To make it your material ready first, and then go to this file option, new and device. From there, you will find these options and make your device from there. I hope you understand. Now, if I would like to import, I want to make it this other application which is not enabled, grain boundary for battery related application and nanowire. For that purpose, I need to create the surface first, surface layer, and build it. The silicon material I took it and make the surface. Then you can see the grain boundary and nanowire. Nanowire crystal radius that is enabled. For nanowire, once I click on it, wire direction, cluster radius, surface energy in 100, 110 and 111, and click on preview. This is nanowire. If you want to increase the cluster radius, you can mention the cluster radius. Size of cluster radius, wire radius has been increased. This is for 110 direction. and 111 bi-direction, and you can build it. And if you will go for this, what I say, grain boundary, you can click on this grain boundary. You can find coincidence site lattice sigma axis theta cos theta. So this is all their points, and select the particular axis theta value and see its preview. This is preview for grain boundary, vector rotation, after rotations. And then you can build it. You can see the orthogonalization, different planes. So there are a lot of features are there. You can build it. This is simple that I have created. If I would like to create some other import, I can go to the import local and go to the example directory. Let's suppose you want to define the material with different electrode positions. So I took this example that I create given as an example in the library, where left gold electrode, right side gold electrode, and in between there is a molecule. From here to here, this is one molecule, malonyl molecule, which is connected with the two metallic gold electrode. If you would like to check the property of the atomic coordinate points, I can do one thing. I can hold the control and draw the rectangle, and then right click on it, click on display atom. In the display atom, you can find the coordinate point and their element name of each atom that exist in this particular structures. So you can see this is from first atom, second atom, third atom, fourth atom, like that, all atom with their XYZ coordinate value. Up to 71 atoms are there total. So definitely you can use the whatever the channel length you want to build. You can build according to your needs. Basically the distance in angstrom, but you can take micro level also. As I think you can try it. It is possible. It looks. And in this region, if you want to define the gate, then simply the procedure is similar to define the transistors. If you want to change any atom, simply just select that particular atom and click on this replace atom. From periodic table, you can choose the element will become changed. From this home button, once I click on home, it will take to my right position. I can rotate anything in any along X, Y, Z, vector, screen view. Any distance can be measured. So these at position which you can see on the top of the screen, that will help you a lot. The builder and toolbar. These two option will help you to create your desired shape. Desired element you can choose and you can manipulate the structures and simulate based on DFT. You can also try some experiment in your computer where the software is installed already. Now I would like to import some of the project because simulation may take some time. So I go to this and click on open project. Go to this user where my some project are present. I have loaded in this particular folder. So you can see these are some folder where I have some project located. So I want to open some of the project that I built in past. So I want to open the silicon.hpf complete project file. It is now loaded. And here, this is single silicon crystal band structure, effective mass that is calculated. So I can click on show view, band structure. And to view the effective mass, we can see in MATLAB. This is single MOS2 crystal, MOS2. If you would like to check the properties, thermoelectric property or jetty related property, in this particular project, I calculated the Phonen property calculations. So this is my MOS2 and I run the calculation. This is Phonen band structures. If you want to check the thermoelectric, I can right click on thermoelectric and click on show view. So this is conductance with respect to temperature variations. So I can decrease the energy points also. On all the energy points, the graphs are plotted. So there are so multiple options are there. We want to see on single energy level point of the conductance. You can also plot it since many of the points are there. If you want to see, you can see there is a plot type. Apart from conductance, you want to see the CV coefficients. So CV coefficient is there on different chemical potentials, chemical potential energy levels. So I can select this chemical potential. This is CV coefficient. If you want to see the thermal conductivity, this is thermal conductivity. On temperature, which temperature? 50 Kelvin, 100 Kelvin, 150 Kelvin, 200 Kelvin, 250 Kelvin. So this one graph is now remaining, which is at 300 Kelvin thermal conductivity. I can zoom this particular regions and see whatever the points you want to do the study, you can do that. And this is a thermal conductivity phononic. So phononic and electronic, both thermal conductivity are possible, including ZT. If you will select the ZT, this is ZT with respect to chemical potential. With respect to temperature, you want to see, This is with respect to temperature. You can see all the different energy value. The thermal conductivity is plotted with temperature variations. So at what particular energy level you want to plot it, you have to select according to your need. This is graphene based device where I created this previously left and right electrode with the device. And we can also simulate it. I would like to open other project. This is another project that I want to see here. This is like different molecule that we have created. Molecular study. And this is one of the device, 4-probe device. The molecule is connected with 4 terminals, so all are gold electrodes. So we have created such kind of device structure. Even vertical, horizontal, whatever you want to create, it can be created. Similarly, this is another one. So left electrode, bottom electrode, 6 electrodes has been generated, 4 electrode has been generated based on different biasing. And the calculation, definitely it will take time dependent on the system. And this is one another silicon crystal where I have calculated some, let's see, density of state with including spin of density of state with minimum 10 to maximum energy range, and spin up, spin down, and both spin up, spin down at a time. This is for Fe. If you want to work on other applications like magnetic related, this is FE magnetic tunnel junction. So the device is already given as an example. Whenever we will run the calculation of this particular magnetic tunnel junction, magnetic property we can also calculate. Spin current, magnetic movement, magnetic texture, atom magnetic movement. So this is Fe, MgO, Fe. So Fe this side, Fe this side, and middle one is magnesium oxide. And all are interconnected together. And this is another ZNO, MgO, ZNO. This is ZNO, MgO, and silicon. And for interface in between two different material, this is nickel graphene heterostructures. These all can be created in the tool. There is another project called double layer graphene. So let me open it. This is double layer graphene, with only two atoms are there. And on different Vicing, the band structure is calculated. At 0 Vicing, at 10 volt. So if there is any variation, we have to look into the particular billion Jones root point. Then only we can be able to measure the band gap on that particular points. If we want to measure the band gap at whenever you will apply some electrical field without applying the electrical field, how much will be the gap? So that gap you can also do the study on different Vicing applications. That's why this is different 0 volt, 2 volt, 20 volt band gap and other molecules are simulated. This is H2 molecular simulation. I want to looking for some project. This is another device. The left electrode, right electrode with hydrogen passivation on the top and bottom side. With white atoms, which you can visualize, these are hydrogen passivated atoms. And the plot output, which is calculated, that you can see. I will right click and click on transmission spectrum. This is transmission coefficient. transmission energy points. If you want to see the Seebeck coefficient, this is Seebeck coefficient with a spin up, spin down with chemical potentials. And all the temperature variations. So Seebeck spin and charge coefficient it can plot, effective potential it can plot. And this is effective potentials. Now if I will go for other project, I can open it, open project. Li to O2 interface. Like this is one device interface that I created in past, and let's see simulation is done or not. Simulation is also done and plotted these different properties. Sorry. Sorry, I have deleted some of the file. That could be the reason. And these are some output by using the rescue tool. So this is a density of state with SPDF. Like that. And projected density of state, band structure, these all can also be calculated. If I will go for this is another device where we have simulated Zn, Zno, and Zn and calculate these property. For IV characteristics, you have to run it on different voltage, and then you will plot single hour value, and then again you have to run on different biasing voltage, and you need to plot it. So I go to the particular project where some optical properties is also there. So you can see this is a optical property where Al2N2 is plotted. Dielectric permittivity is there with respect to energy. And if you want to see the IR intensity, I can click on this next file, which is plotting the IR intensity. And this is for energy loss with respect to energy. And if you want to see the optical refractive index, real and imaginary part of the refractive index is calculated. So this is basically calculated in plotted in MATLAB, but simulation is done by using the RESCU code, this AL2N2. If I plot other parameter by using the tool, I can load whole project window and go there. Now you can see this dielectric permittivity again, and some Raman property is also there in this particular project. IR intensity, and this is polarized Raman intensity shift. And this is averaged Q1 Raman intensity plot. So this is calculated using RESCU. It is already available in my tutorial. If I will go for Graphene, and this is electronic band structure by using the RESCU tool. If you want to see the density of state, this is electronic density of state, and this is PDOS. This is PDOS plot and projected density of states input. So PDOS is there, DOS is there, band structure is there. Everything can be done by using RESCU as well, with hybrid functionals are included. And this is for Ni2O2 density of state plot, and Ni2O2 density of state with Howard U. This is with Howard U plot. All plots are there. You can see these are all plots available. And even other property which you are looking for, all the effective masks and other property can also be calculated. I would like to show you here. This is effective mass.mesh file. I can click and See here. We can also construct the effective mass and other things that can also be calculated. Energy in MATLAB, many of the output are there in MATLAB formats. It can plot all this parameter. So many of the things are there. Even you can also try at yourself so that you can find all the things which you are looking for. So I think I have tried to explain a lot of things. Even if you have just questions, I can take the questions as well. So the NIO2 is showing metallic. The DOS is not looking as usual DOS plot. What is the accuracy rate of the software? Can you please explain? A little bit confused. So basically, the output based on you know the output is always depend on the input. Okay, we have taken as an example, and license is given to verify. Even you can go to the that papers on the this open source library. You can type NanoDCAL and then type the DOS properties. You can find the DOS property and find the accuracy. So accuracy, the paper is the best solution to find the accurate property of the particular product. Because a lot of papers have published, it means it is verified. You can also look into the website and go to the technical insights. And here some of the things are present in terms of paper publication. May not be some of the recent, but you can find yes, some of the papers are there. So either on the website or on the Google Scholar. Simply NanoDCAL type the name of the product with the property that you are looking for. It will come it. So you can try to use this application for gas sensing. We have not used it, but once you will try, maybe it will be helpful for your needs. Just you have to try. So we have given the license already multiple times and already told you the installation procedure. If anybody have any problem, you can also contact to us by email, by call. So once again, all the things are there. Now I request to participant kindly unmute your mic. You can ask your queries. For more information, you can visit our YouTube channel, and you can go to the documentation page. I can refer you the website, license is given to you. The practice need to be done by you. So this nanoacademic.com website, you can go and scroll down. And once you will scroll it, you will find some documentation and tutorial. And click on this NanoDCAL. You can find tutorials here. And many video is already prepared. So once you will follow these video, you can easily create your structures.
Hello,
Yes, please.
sir. My voice is going. Sir, I want to ask that
Yes,
can we,
I cannot able.
sir, as we you have plotted two types of electrode in this tutorial, but sir, can I ask that can we model a battery by using
Yes.
two electrode and electrolytes?
Yes, you can model it according to your need. If you want to use different material, you can use it.
Sir, I want to see one IV characteristics plotting.
Mm-hmm.
IV characteristics. One example
Yeah,
for IV.
IB is also possible. So you have to run the calculations,
Sir,
and on it will generate. 1 minute, 1 minute.
if
Let me show
possible,
you.
sir.
Just a minute. Just a minute.
Hello.
This is one of the video where IB is calculated by using the software. So let's open it. This is specifically for IV calculation. So first of all, we import the material. So these are different material, as I already told you. So this Graphene Nanoribbon device we have built and defining the electrodes. And see the preview. The device is getting ready. The electrode, left and right electrode is defined and it's now built. We will calculate the IV characteristics in this particular things. Go to NanoDCAL and click on SCF calculations. Here we will define the electron temperature, energy cutoff, exchange correlation functions, contour integral, electrodes, left electrode and right electrode with their temperature and voltage integration control parameters, basis sets, spin type. Whatever feature I need to enable it, we have to select and enable that particular features. And then click on generate files. Now there are three folders created: left electrode, right electrode, and device one. So device is basically a total. The output of electrode will be assigned in this device script file. It is automatically generated script where there are two electrodes are there. Left and right electrode is there, and it is make a complete device file. Left side it is a electrode material file, and I can run it first the electrode one. Click on run button. Now the calculation is running. Similarly, we can also run this right electrode and also run the device. So all are running, left and right one. Log file is generated. In the NanoDCAL, we will go to the analysis one. Here we will select the required output. So device output and electrode material output, both are possible. So we can select the density of state, total energy, scattering, transmission, photocurrent, IV curve, okay, electron density or whatever. And there specific parameter is there that we can define it. Now once it is done, we can also create the another project with different vicing. So you can see there are two projects created at 0 vicing and 0.2 vicing. The voltage we have applied in the file, input file, where it was applied. So I would like to tell you. You can see here SCF calculation. Here we will apply 0.2 on the electrode side. You can see here the 0.2 voltage applied. First one at without any vicing voltage, it is at 0.2 at right electrode. So you can see there are two HZW file, main HZW file. Accordingly, the whole project will be generated. Simulator and analysis part, select the IV and click on generate file. Now the IV, we have selected it. And we will create another project at 0.4 voltage. The name of project is changed and we can define the voltage is equal to 0.4. And define the collinear spin and click on generate file. So 0 volt, 0.2 volt, 0.4 volt. Similarly, I have to select that IV curve, analysis one, and generate the file. And another one project I want to create at 0.6 volt. So here I will change the right electrode voltage and spin type to collinear spin and click on generate file. So there are four projects 0, 0.2, 0.4, 0.6 has generated, and select the IV curve.input file for this project as well. So for different project at different vicing has generated, I want to create another one at 0.8 volt. So that 0, 0.2, 0.4, 0.6, 0.8, we can plot the IV, multiple vicing voltage, and change here the voltage. Click on generate. And similarly select the required IV curve dot input file. And 0 to 1 volt completely, all project will be there. 0 to 1 volt. That's why the same procedure is going to be applied. Multiple project will be created and you can change all those things. Now the simulation we have run it, because you know the when I will run the live, it may take some time. We have already run it in past and see the other property at 0 biasing voltage. This is density of state. With the spin up, spin down, and both spin up, spin down at a time. Similarly, the transmission coefficient, spin up, spin down, both and total. And then we'll go for the IV curve as well. This is total electron density. Along X, Y, Z directions. And Bundy plot. And Seaway coefficients. This is Seaway coefficient on different chemical potentials. Action correlation.
Excuse me, sir. Am I audible? I am Akash.
And current voltage curve .xml file is there, but here it will not generate the output. We have to go to the MATLAB and load that project. So we will locate this device studio Graphene folder where all our projects are there: 0 volt, 0.2, 0.6, 0.8 and 1 volt. So you can see these are all projects are loaded in MATLAB. So this is current voltage curve.mat file is there. Mat file, MATLAB. I will click on data. Now you can see voltage equal to 0 where we have got some current value. V1 equal to 0 and I1 equal to something value. V2 equal to 0.2 and current equal to something value. So similarly, we have to plot and measure the value that we have got on different biasing. V1, V2, I1, I2 are there with spin decomposed conductance and descriptions. And let's open at 0.4 volt that project current voltage curve.mat file. This will be at 0.4 volt on V2 terminal. So click on data. V1 is still 0, I1 equal to something value, and V2 equal to 0.4. The current voltage curve.mat file will be generated by the tool. And we will type and find the spin decomposed spin related parameter as well. And we will combine all this value on different voltage, the different current, and we will plot in MATLAB. So you can see in the third one, the V1 equal to still 0 and V2 equal to 0.6 and current is changing.
Can you hear me, sir? Excuse me, sir.
And similarly, we will make a new script and define here the value that we have got it on that different value and plot the spin current and IV. So V1 is equal to 0 0.0, 0 0.2, 0 0.3, 0 0.4, 0.2468. So we have to define this, whatever we have calculated, mention here the input value of gate voltage and similarly the current that we have calculated. So we have to put it in this new script. This is plotted. So this is all calculated value. I equal to I spin equal to I spin down equal to I2 equal to I spin up equal to spin down equal to, and that's why it will plot. This will plot the spin up, spin down, and without any spin, current voltage. This is all calculated value on different voltage, and then we'll click on run. Now you can see this is a graph. So this graph can be calculated with various voltage wise without any spin, normal condition, spin up condition, and spin down condition. Thank you very much from my side.